Thanks for Dr. Weglein introduction, and thanks for coming on our annual meeting. Today I will try to incorporate the source wavelet and reading pattern into our RSS multiple removal algorithm. I will show how to incorporate them. In my talk, first I will talk about why we do this job, and next I will review the impact of reading pattern on removing free surface multiple when a multiple interferes with the primary. And next I will talk about the internal multiple attenuation algorithm and how to incorporate the source wavelet and reading pattern. Next is my conceptual data type. Finally is my conclusion. As seismic exploration moves to increasingly complex geology, multiples can often be proximal to or interfering with primaries. This situation can happen in many marine cases and frequently happens in onshore places. Hence, it is a big challenge to remove multiples without damaging primaries. In current standard practice, after multiple prediction, the adaptive subtraction is often called up to remove multiples. This adaptive subtraction works very well for isolated events. It can fail for proximal or overlapping events. So to address this challenge, we want the multiple algorithms can predict exactly the phase and amplitude of all multiples at all offsets, and thereby we can surgically remove them directly and without subsurface information and without damaging our primaries. The current delivery of RSS method can eliminate the free surface multiples and attenuate internal multiples directly and without requiring any subsurface information. However, to deliver the promise, the prerequisites have to be satisfied. The prerequisites include the removal of the reference wave field and an estimation of the source wavelet and the radiation pattern and the source and receiver deghosting. In morning's talk, Dr. Jinlong have shown that the impact of the prerequisites on the multiple removal method. And in Linpang and Jinlong's talk, they talk about how to predict and remove the reference wave field. And in Jinlong's talk, they also talked about the source and receiver deghosting. In my talk, I will focus on how to incorporate the source wavelet and the radiation pattern into the multiple removal method, including the free surface multiple removal and internal multiple removal. As we know, the current RSS multiple removal method assumes that the source is an isotropic point source. In my talk, to improve the effectiveness of RSS method, I will incorporate the influence of the source wavelet and the radiation pattern into RSS method for the data generated by a general source with a radiation pattern. Because for marine case, the source array have a radiation pattern. Even for a single air gun, there's a radiation pattern. First, I will review the impact on the free surface multiple removal. This work is done previous year, and I will give a brief review on how to remove a multiple that are interfering with the primary. In this part, I modified and extended the RSS free surface multiple elimination algorithm that is pioneered by Dr. Carvalho in 1992. And by accommodating a source array with a radiation pattern. And also I showed in the numerical test that the modified algorithm is fully data driven and doesn't require any subsurface information. And in principle, it has the ability to predict exact free surface multiples at all offsets for source array data with interfering events. As we know, in our RSS method, the actual medium is a reference medium plus a perturbation. The wave travels in the reference medium, we call it a reference wave. And the wave travels in the actual medium, we call it a actual wave or total wave. First, we want to separate the total wave into reference wave and scattered wave. The scattered wave is the difference between the actual and the reference wave. This is our RSS typical processing flow. First, this is our measured data on the surface, the total wave field. First, we apply the green theorem to separate into the reference medium, reference wave, and the scattered wave. After the separation, we will use our deghosting green theorem deghosting method to deghost the scattered wave, the receiver deghost, and the source deghost. This in Yingtang and Jinlong talk, when they get the reference wave, they can get the source signature A omega. But for the general case, if the source is a source array or source generator with a radiation pattern, I need to get a further step to get the direct reference wave. And next step, I will use this to get the source signature of the radiation pattern. After that, I will input our free surface multiple elimination algorithm to remove free surface multiples, and then input the internal multiple algorithm to attenuate or remove internal multiples. I will, in the tutorial, in Dr. Weglein tutorial of Jinlong talk, they also mentioned the green theorem wave separation method. Here I just give a very brief summary how to get the reference wave, scatter wave, and how to deghost them. Choosing a half space of water, this work is done by Dr. Weglein and secret in 1990 and pioneered by Jinlong and also further developed by Dr. Mehan. First, we choose the reference is a half space water plus a half space of air, and we can get the reference wave and the scatter wave by the green theorem method. And if we choose the predict point below the cable, we can get the reference wave. This is the surface integral. If we need, in this integral, we need to know the wave field on the measured surface and the derivative on the measured surface. We can get the reference wave. Similarly, using the same surface integral, if we choose the predicted point above the cable, we can get the scattered wave field, Ts. It's the same surface integral. Only the difference is the prediction point is above or below. After that, we want to deghost our scattered wave field. Also, we want to get the direct reference wave field. This time, we choose different reference medium. It means that we choose the Green's function is different. This time we chose the whole space of water as the reference medium, so we can remove the ghosts using Green's theorem. Similarly, it's also the surface integral, but the Green function is different. Here the Green function is the whole space of water, a called Green function. This we will get the receiver side deghosting data. After that, we using the reciprocity, we switch the source and the receiver coordinates, applying this surface integral again, and the source deghosts can be removed. Similarly, the reference wave P0 can be deghosted to obtain the direct reference wave field P0D. After getting this, next step, we want to get the source signature of the radiation pattern. How to get the source signature? The direct reference wave can also be expressed as the integral of Green function over all ions in an array. It can be written in this case. For a special case, for the anisotropic point source, this equation can reduce to P0D equals the multiplication. So this will simply to get the point source signature. For a general case, we can use the bilinear form of Green function and forward transform over all receiver. We can obtain the projection of the source signature in terms of the direct reference wave field P0D. For a 2D case, after the forward transform, we can get a relationship between P0D and rho. This rho is the only projection of the source distribution function. We have this constant. Since this constant 1 over Q and K and Q is not a free variable, so we cannot get the total wave field, total source signature in the X omega domain. But the projection can always be achieved from the direct reference wave field P0D. And this Q of K represents the amplitude variation of the source with angle. Next step, we got here we assume we got the source and the receiver deghost data, and also we get the source signature of radiation pattern. Next step, I will put this into our free surface multiple elimination subseries. We can get the free surface multiple elimination algorithm. This is a summary of this algorithm. The left side is we call current algorithm is proposed by Dr. Carvalho in 1992. It designed for the point source. Here A omega is the source signature for the point source, and we already get the deghost data and put it into our algorithm. We can predict the free surface multiple order by order, and finally we can sum them together. We can get the free surface multiple data. Similarly, if we have a source array data or the data with the radiation pattern, we need to incorporate the projection of the source signature. And you can see this is outside of the interval, this is inside of the interval. And we can also calculate the free surface multiple order by order. And finally get the free surface multiple data. Next, based on this, I will show some synthetic data test. In this algorithm, the free surface multiple elimination algorithm is constant with the Green's theorem method. They are multidimensional and do not require any subsurface information. And they only require the projection with source signature and the deghost data. The modified algorithm is also constant with the current one, with the source array reduced to a point source. In the later scenario test for the point source data, the current algorithm is sufficient to predict the exact phase and amplitude of the free surface multiples. But for data generated by a general source with a radiation pattern, our current algorithm is not sufficient. Our modified algorithm can predict a more accurate result. This example, a very simple example, just to show my algorithm works. This is first I want to show this is only one reflector at the water bottom. Due to the water bottom is very shallow, only 90 meters, so the primary and the multiples are overlapping. I will put two kinds of source. First is the point source, another is the source array. For the point source, I want to show our current algorithm has the ability to predict the exact phase and amplitude of free surface multiple. And for the source array data, I want to show the modified algorithm can predict and remove free surface multiples completely. First, let's look at the point source data. This data is generated by Carney-Hooke method, so we can choose only the events we are interested in. In this example, I only generated two events. First is the primary, and another is the first order free surface multiple. There is no ghost in this data, so it means we already removed the ghost. The right hand side is the box piece. You can see the primary and the multiples are overlapping. After free surface multiple removal using Dr. Carvalho's method, you can see all multiple free surface multiples are removed. Look at the back and forth. You can see they removed completely without adaptive subtraction. We can surgically remove them through a simple subtraction. Next, I will pick a trace to look at some detail. This is the input data at the offset 1800. This is one trace. You can see the primary and the multiples are overlapping. You cannot see which one is multiple or primary. After free surface multiple removal using the Carvalho's algorithm, this is the primary. Because the Carney-Hooke method can also generate only the primary, so we can compare this result with the generated primary. This is generated primary, so we can look back and forth. You can not see any difference. It means our current algorithm has the ability to predict and remove free surface multiples completely. If I put the three events together, you can see this. The blue one is the input data. The green dash one is after free surface multiple removal. The red one is the primary, generated primary. Next, I will show if it's a source array data or the data with the radiation pattern. This is the data. It's the same, also generated using Carney-Hooke method. The first is the primary, the second is the first order free surface multiples. The right hand side is this one is the primary, this is the free surface multiple. You can see they are overlapping. After removing the free surface multiple using Dr. Carvalho's method, this is the result. You can see there's still some very weak residue. You can see here the residues. If we use a modified algorithm, this is the result. You can see all the multiples are removed completely. In this example, it shows that our modified algorithm can handle the source array data with the radiation pattern. I also pick one trace to look at the detail. This is a residue. If we use current algorithm, this is a residue. And if we use modified algorithm to remove free surface multiples, there is no visible difference. To look at the detail, I choose also the offset at 1800 meter trace. This is a generated primary. Next, I will show the result using current algorithm. This is the result using current algorithm. You can see the residue is here, and the amplitude is a little weaker than the generated primary. Next, if we use modified algorithm, this is the result. And also, we compare this one with the generated primary. This is the generated primary. This is the this after free surface multiples removed using modified algorithm. You can see there is no difference. If we plot them together, you can see if we use the current algorithm, there is some residue, and also the amplitude is a little weak than the generated primary. If we use the modified algorithm, the multiples can be removed completely. These two examples show that if the data is generated by a general source with radiation pattern, our modified algorithm can handle this situation and can remove the multiples without any adaptive subtraction. You can surgically remove them. This is also our objective. This is a summary of the free surface multiple part. And in this part, we modified and extended this free surface multiple elimination algorithm by incorporating the source array. And this algorithm does not need any subsurface information. And the numerical tests show that with overlapping events, the modified algorithm has the ability to predict and remove free surface multiples at all offsets directly without any subsurface information. Next, I will want to also incorporate the radiation pattern influence into the internal multiple case. As I said in our processing flow, after free surface multiple removal, we can input this data into our internal multiple algorithm. So our internal multiple algorithm assumes that the ghosts have been removed and the free surface multiples have been removed. Assume in a 2D case, this is our measured surface data. This is in XG, XS, T domain. In this data, there is no ghosts, no free surface multiples. First, we need to forward transform this data into K omega domain. And we define B1 by multiplication 2 minus 2I QS. And also, we water speed migration this B1 into BKKZ domain. This is the input of our internal multiple attenuation algorithm. The attenuation algorithm is proposed by Arroyo in 1994 and Dr. Weglein in 1997 and 2003. This algorithm, we need to have 5 intervals. This is a 2D case. And KSKT omega is a horizontal wave number and frequency. And GQS is a vertical wave number. And Z1, Z2, Z3 is a pseudo depth. It's a water speed migration of our input data. and the epsilon is chosen to this algorithm satisfy the lower, higher, lower requirement. This is a verbal description of previous slide. How to get the B1 from the first equation in our inverse scaling series? We have data equals G0D V1 P0D. This one assumes that this is a general source case. For unit source case, this is G0D V1 P0. If we write in the 2D case, we can write in the explicitly. For unit source, we know P0D is a G0D. It means the source wavelet is A omega is 1. And we can take a forward transform in the previous equation. We can define B1 is this, is minus 2IQS times D. For an isotropic point source, the P0D is the multiplication of A omega G0D. Similarly, we can define B1 is this by this deconvolution. For a general source with a radiation pattern, P0D is the integral. We cannot directly derive by G0D, but after Fourier transform, this case is rho we already obtained in the previous slide. In the K omega domain, this is a multiplication. And here rho is a projection of the source signature, which can be solved from the P0D. So after getting the input of the internal multiple attenuation algorithm, we can input B1 into the previous slide to get B3. Similarly, after get B3, we need to combine this source signature back of the projection of the source signature back to get the data to compare with the original input data. In this derivation, we can see that the modified ISS internal multiple attenuation algorithm have benefits because we do not need to change any the kernel of the algorithm. The code do not need to change. The source wavelet and the radiation pattern is incorporated by the input B1 and output B3. Next, I will show some examples. First, I want to show this example is already shown in Dr. Mehan's slide. This shows the impact of the source wavelet on the internal multiple attenuation. This is two reflector in this example. And the data is generated by finite difference method. The left-hand side is the input data. This is first primary, second primary, the first order internal multiple and second order internal multiple. If we apply the current algorithm without a wavelet deconvolution, the right-hand side is a prediction. We can see the amplitude, the phase is correct, but the amplitude is totally different, and the shape is different. So we cannot easily to subtract directly from this data. But if we incorporate in the source wavelet deconvolution, our prediction is like this. You can see the phase is still correct, but the amplitude is very close, and the shape moving closer. I will pick some traces to look at some detail. This is a middle trace. The left side is the internal multiple in the input data. It looks like this. The right-hand side is the predicted internal multiple using our current algorithm without a wavelet deconvolution. You can see the shape is different, and the amplitude also different. If we use the algorithm with wavelet deconvolution. This is a prediction. And if we put them together, we plot them together, this is a difference. The red one is the input, the internal multiple in the input data, and the green one, the blue one is the predicted internal multiple. They are matched well in the zero offset. If we also compare the different offset at the 1700 meters. This is the input internal multiple. This is the prediction. They match well for the shape and the amplitude. Next, I will using the source array data to show the impact of radiation pattern on the internal multiple attenuation. We use the same model, but I use the source array data. This source array data have 5-point sources. The range is 20 meters. It's not very big, so that's why our impact is not significant. But you will still see the difference. The left side is input data generated by finite difference method. The primary internal multiple. The right hand side is a predicted internal multiple. First because we want to separate the issue. So this prediction, we assume that the wavelet already removed. Otherwise, this is too different. We cannot see the difference. And without incorporating the radiation pattern. Next, if the algorithm predicted internal multiple using an algorithm incorporating the radiation pattern, it looks like this. For these two slides, you cannot see any visible difference. Next, I will show the difference. I subtract them together. You can see this is the difference. Next, I will show some detail. I pick the middle trace and far offset trace. This is the middle trace. In the middle trace is not there is no visible difference. The red one is the internal multiple in the input data, and the blue one is the predicted internal multiple without a radiation pattern, and the green dash one is the predicted internal multiple with incorporating radiation pattern. At the zero offset, there is no big difference because because the symmetry of the source in the middle. At the far offset, a red one is internal multiple in the data, and the blue one is predicted internal multiple without incorporating the radiation pattern, and the green dash one is predicted internal multiple with incorporating. This is the difference you can see. Because our source array, the radiation pattern is very smooth, that's why there is very little difference. But from this example, we can show that incorporating the source wavelet, the amplitude and the shape of the internal multiple can significantly improve. Incorporating wavelet and radiation pattern, the amplitude can further improve. This is the conclusion I just said. Because in my test, the source array have a very smooth radiation pattern. In the real case, look at some example. I picked it from 2 papers. This is the radiation pattern of ion array. The horizontal one is the frequency. So the circles represents the different frequency. And this represents the different angle. And the color represents the different amplitude. So for the source array case, we can see at a different amplitude, a different angle and different frequency, we have a different amplitude. For the line case, I found one case is like this. This is a normalized displacement, and this is the angle. This curve represents different amplitude along the angle. So this is a rapid change in the radiation pattern. So next step in my future work, I will looking at what difference are made if we include this kind of real radiation pattern in our demultiple algorithm. If we have this kind of radiation pattern, what you can do? Just follow our processing flow. From the measured data, we can first separate wave into reference and scatter wave, and then further we can degauss them. We can get the radiation pattern or the source signature, and then we remove free surface multiple. Next step, we remove the internal multiples. Follow these steps, we can incorporate the source wavelet and the radiation pattern in our algorithm. We can predict more reliable multiples. Finally, I want to summarize this talk. First, I extended and modified the free surface multiple elimination algorithm, and tested on the data with overlapping events. And also, I modified and extended the internal multiple algorithm by incorporating the source wavelet and the radiation pattern. And the code development of our group can be found in our website. It's a sponsor-only website to get the code. And most of the code are available to use. The green theorem preprocessing code, and RS free surface and internal multiple removal code. And this combination can be will be available within 6 months. Finally, I want to thank all our sponsors and thank Dr. Weglein for his guidance. And thanks for your attention.